So now for problem number 37, it says what plate separation is required for a parallel plate capacitor of 9 nanofarad if the plate area is 0.425 meters cubed, or squared, I'm sorry. Remember that this remember that nano really means 10 to the negative 9. Okay? So somewhere in your notes, you should know that the capacitance for something is equal to E naught, which was like that 1 over 4 pi k, the constant k, right? That's equal to E naught. And that has a numerical value. We'll plug that in a second. But it's E naught times the area over the distance. Okay? And the area is like, these plates are like a square, so we're talking about the area, okay, between the two plates. And we're hoping that because they're parallel, they're uniformly the same shape, equal distribution of charge across the plates and all those things. Those are the assumptions that we're making. But anyways, this is the formula, this right here. That's the formula. And so this epsilon naught is a constant, and that could be written as, if you do the math, it's just easier because this really never changes too much. So then that is 8.85 times 10 to the negative 12. And this is a weird one. It's like coulombs squared per Newton meters squared. Okay. Did I write that down right? Yeah, that's right. So now if I take this equation, what are they asking for? What is the separation? Well, the separation is D, right? And they've given us A. So if I solve for D, I'm going to multiply. So D comes over here, and then I'm going to divide both sides by C. So it should be E epsilon naught A all over capacitance. Let me double check that, make sure that's doing my math here in my head. Yeah, that's right. So what's A? Well, A is the area. It's in meters cubed, right? So that's right. A is equal to 4.25 meters cubed. That's good. Proper units. Epsilon we have right here. And then capacitance is really 9 times 10 to the negative 9 Faraday. Okay. So to finish this problem, we just got to plug it in. So we say that the distance should be equal to 8.85 times 10 to the negative 12. And I'm just going to, as long as I make sure that I have my units right, I don't necessarily, at this point, we should be able to just write the magnitudes down and things should cancel. And if the answer doesn't work out right or it seems weird, then you go back and do the dimensional analysis, but I just don't have room on my whiteboard. So I'm going to multiply that by the cross-sectional area, which is 0.425. And then that's divided by the capacitance, which is 9 times 10 to the negative 9. And if you plug that in your calculator, you should get 4.18 times 10 to the negative 4 meters. And I think your textbook, for whatever reason, probably because it's an easier way to measure it, like who measures, like if you were to make this capacitor, like who measures times 10 to the negative 4? So we want to make that in a measurement that we can actually use. And so we could convert this to, like, say, millimeters. And if you do that, it would be 0.418 millimeters. Still, that's kind of difficult, but this is probably a more practical measurement. The two mean the same thing. But that's the answer.